Okay guys, welcome back to our channel. In today's class, we're going to be looking at nomenclature of organic compounds. Okay, but before we actually dive into nomenclature of organic compounds, it's first we look at the classifications of organic compounds. Organic compounds can be classified based on the functional groups and based on the structure. So basically what we're going to be looking at today is classification based on the structure. Right, the two broad classification based on structure is classification based on the whether it is open chain or whether it is closed chain. All right, another name for open chains are called acyclic. Another name for closed chains are called cyclic. So if you look at this, this is open chain and this is closed chain. So what we're going to be doing today is going to be the open chain, and the first member we have the alkane, we have alkanes, we have alkenes, and we have alkynes. Please, before we proceed, please, if you're a new subscriber, please kindly hit the subscribe button below. Thank you very much. Please, before you proceed, just pay like 1 second to hit the subscribe button. And for returning subscribers, thank you very much for always coming back to watch our videos. Okay, since we've established the types of open chains we're going to be looking at, we have alkanes, alkanes, and alkynes. So let's dive into this. Okay, the first hydrocarbon we're going to be looking at today is actually alkanes. Now, you may want to ask yourself, what is an alkane? Alkane is actually a saturated hydrocarbon. Sorry, I had to saturated alkane. It's a saturated hydrocarbon with a general formula of CnH2n plus 2. Okay, so that's the formula for alkanes. We said it's a saturated hydrocarbons with a general formula of CnH2n plus 2, where N is equal to the number of carbons. Okay, it's very important for us to point out that if you must understand how to name a compound, alkanes can have a straight chain, that's the normal chain alkanes, and it can also have a branch chain. Now, the normal chain alkanes do have a general names depending on the number of carbon atoms. So this N is the number of carbons. Alkanes with first 1 carbon atom. If you insert 1 here, this place you're seeing N. If you put 1 here, that becomes C1. 2 times 1 is 2 plus 2 is 4. So the first member of alkane series is CH4. All right, so the name of this first member is methane. Okay, so this condensed formula for methane is the same as the molecular formula. Okay, you realize that as we move down, as the number of carbon increases to 2, the formula here becomes C2H6. How did we get C2H6? Anyway, we see N here, we're going to insert 2 here. All right, so this becomes C2, and anyway you see N here, you put 2. 2 times 2 is 4, plus 2 is 6. So we got this. All right, so in a condensed form, so we're going to have CH3. You may want to ask, how did we arrive at CH3? It's actually very simple. If I'm to, now since they said it's 2 carbon, you write the first carbon, you write the second carbon, you join the line here, right? You realize that this carbon is always a trivalent in nature. Carbon is always supposed to have 4 bonds. So far we can just see 1 bond here. So the remaining 3 bonds will be occupied by hydrogen, and this other one occupied by hydrogen. So that is how we got CH3. So the name of that guy is ethane. All right, so we continue. If the number of carbons increase to 3, we have C3H8, and of course if you look at the condensed formula, we have this condensed formula in the sense that we are not showing the bond, right? CH3, CH2, CH3. If you count the number of carbons here, is going to give us 3, and if we count the number of hydrogen here, it's going to give us 8, and that's propane. All right, so alkane with 4 carbon chain, straight chain, is butane. Now, it's very important for us to know that for you to understand how to name a branch chain alkane, that's alkanes that has a substituent, you must know the normal alkanes. What do we mean normal alkanes? Alkanes that do not have branches, right? Unbranched, or perhaps a straight chain. All right, so straight chain alkanes with 2 carbon atoms is called ethane. Straight chain alkanes with 5 carbon atoms is called pentane. Straight chain alkanes with 8 carbon atoms is called octane. All right, so if you actually, we also have if you take a look at this, 9, when the number of carbon gets to 9, we have C9 H20. Now, how did we get this H20? If you actually put 9 here, if you put 9, this becomes C9. 2 times 9 is 8, plus 2 is 20. So if you follow this formula, you're going to arrive at all of this. So if it is 9 carbon atoms, we have nonane. If it is 10 carbon atoms, we have decane. If it is 11 carbon atoms, we have undecane. If it is 12 carbon atoms, we have dodecane. Okay, so you might want to pause this video and then go back again to check through how we got all of this. Do not forget that alkanes are saturated hydrocarbons. You may want to ask yourself, what is a saturated hydrocarbon? Basically, when a hydrocarbon is saturated, it simply means that that particular compound, hydrocarbon, do not have a double bond or a triple bond. So it's basically only single bonds all through. All right, so what is hydrocarbon as well? Hydrocarbons are compounds that contain specifically only hydrogens and carbon. As the name implies, hydrocarbon, hydrogen and carbon. Okay, now let's look at how to name branched chain or substituted alkanes. There are basic rules that you must take into consideration when naming alkanes, and I had to summarize those. They are very lengthy, but I just had to summarize them to 6 or 7. So rule number 1 says that you should select the longest chain, which is a parent chain. Anytime you're asked to solve, anytime you're asked to give a name of a compound, the very first thing you need to do is to identify the parent chain. The parent chain is the longest continuous. All right, longest continuous simply means it has more number of carbon atoms and it continues. It must not necessarily be always the horizontal. You know, oftentimes people might just assume to say, oh, the parent chain must always be horizontal. No, if you check this horizontal, this is carbon 1, carbon 2, carbon 3, carbon 4, 5, 6, 7, 8. Right, this horizontal has 8 carbon atoms. But if you count it and go down, which is 1, 2, 3, 4, 5, 6, 7, 8, 9. Right, so you realize that if you realize that this is actually a bit this is longer. This is longer. So you might want to ask, how did we get that? You just simply said this is 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, so this happens to be the parent chain because it is the longest. All right, so this becomes the parent chain. So if you're asked to name this, it simply means that this other part would be a substituent or a branch. Okay, now if you look at the second example, here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This guy is 10. So we also have 1, 2, 3, 4, 5, 6, 7, 8. All right, so remember, if you must get the parent chain, is always the longest continuous. It may actually be the one on the horizontal axis, or it could be the one on the horizontal running through vertical and then going down, as long as it is still continually moving. All right, so in this case now you realize that this is carbon 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. All right, so that simply means that this and this are substituents. Now, after you must have finished identifying your parent chain, the longest continuous, every other thing that is actually not part of that parent chain becomes a substituent or a branch. Okay. Now, if you remember, in the case of the previous one we did, now let's go back to this. In this case now, all of them, it was on branch. This is the normal alkane. This particular one now do not need any rule. You don't need any rule to actually know this. The name is already constant. The alkane that has 2 carbon atoms on branch, this ethane. The one that has 5 carbon atoms straight chain is pentane. Do you get? So is going to form the basis upon which we're going to understand it when it is branched. So you cannot understand how to name a branched chain alkanes if you do not know how to name the unbranched. And in naming the unbranched, there are no rules. It's quite straightforward and constant. Okay, so we are done seeing how we can identify the parent chain. So that's rule number 1. Remember, rule 1, you must identify your parent chain. What is your parent chain? The longest continuous chain. All right. Now, there are ways people can write compounds other than the carbon-hydrogen pattern, right? So oftentimes you might see compounds represented in a line formula, right? So this particular method is called the line formula. So this is line formula. And in line formula, we said every end of lines intersection vertex represents carbon. So in this compound here now, all these points you're seeing, all these places you're seeing red dots, they are all carbon because we said every end of line, and end of line is carbon 1 and carbon 8, right? So those carbon 1 and carbon 8 are end of lines, all right? So they are carbons, and also this particular point, this point I just circled now, is a carbon. So every end of line is actually a carbon. And we said every vertex or intersection. Now, this point is a vertex or intersection where 2 or 3 lines meet. So these points are all carbon atoms. Okay, in addition to this end of line. So when we interpreted this line formula into the normal form that many of us are very familiar with, you realize that this is carbon 1, this is carbon 1, this carbon 1 is this, and this is carbon 2, this is carbon 3, this is carbon 4. If you notice in the line formula, carbon 4 has a projection pointing out. Do not forget that the projection, the end of that line, is actually a carbon atom. However, the line here is the bond that is joining this carbon to this particular carbon 4. All right, so we have carbon 5, which is this. We have carbon 6. We have carbon 7. And we have carbon 8. All right, so this is the interpretation of this. But there is one important thing I would like to state also. In line formulas, hydrogens do not really show. Hydrogen does not really appear. It's only lines. That is why it's called line formula, or some other time you could call it skeletal formula. But when you're interpreting line formula into a normal form, you must actually not leave it like this. You must show the hydrogens, okay, on each carbon atoms, because anybody that sees this invariably knows the number of hydrogen that is here, which I'm going to show shortly. So for you to know the number of hydrogens present on each particular carbons, all right, so we're going to be showing it in this particular representation. If you look at the right hand side, I already did it, but I'm still going to explain. The hydrogens are the ones on this sky blue marker. Okay, so if we actually want to get the number of hydrogens that would be present on a particular carbon, you simply subtract the number of lines or the number of bonds making contact with each of those carbon from 4. Now, why are we subtracting the number of lines from 4? Because carbon can take maximum maximum of 4 bonds. All right. So when you come to carbon 1, let's use this. This is carbon 1, this is carbon 2, this is carbon 3, this is carbon 4, 5, 6, 7, and 8. Now, quickly look through the left hand side. If you look at the left hand side, the hydrogens were not indicated. All right, so we want to now start adding the hydrogens. Now, if you look at carbon 1 here, look at this carbon 1 here. Carbon 1 has just one line, right? It has just one line, this line, right, making contact with carbon 1. So for us to know the number of hydrogen present on carbon 1, we're going to subtract the number of lines making contact with carbon 1. As you can see, the number of lines making contact with carbon 1 is just one line. Okay, so 4 minus 1 is going to give us 3. So therefore, the number of hydrogens that would be on carbon 1 would be 3 hydrogens, hence CH3. Do not forget that we said in line formulas, hydrogens are not always shown, right? So if you want to interpret this into the normal form, you must always add the hydrogens. You can't leave it like this. If you leave it like this, definitely they might mark you wrong, because carbon is very obvious that carbon is lacking exact number of bonds, but in skeletal formula it is always assumed that there is hydrogen present, right, where necessary. All right, so if you look at carbon 2 here, carbon 2 has 2 lines, one on the left and one on the right. So carbon 2 has 2 lines making contact with it. All right, so in order for us to know the number of hydrogens that will be present on carbon 2, we're going to subtract the number of lines on carbon 2 from 4. All right, so 4 minus 2 would give us 2. So that is why we have CH2 on carbon 2. Carbon 3 will do the same thing. Carbon 3 has 2 bonds, left and right, flanking this carbon 3. So for us to know the number of hydrogens that will be present on carbon 3, very simple. We subtract the number of lines seen on this carbon 3 from 4. So carbon 3, you can see we have 2 lines. All right, so 4 minus 2 is going to give us 2. So hence carbon 3 is having 2 lines. All right, now you look at carbon 4. Carbon 4 has 3 lines, the left, the right, and up. So carbon 4 is actually attached to 3 lines. So the number of hydrogens that would be present on carbon 4 is going to be 4 minus the number of lines making contact with carbon 4. And the number of lines making contact with carbon 4 is 3 lines. All right, so 4 minus 3 is 1. That is why we have 1 here. So you continue the process, and then if you look at this carbon here, this carbon is a substituent. All right, it's a substituent. If you look at this carbon here, you realize that this carbon has just 1 line. That's the one that is joining it with this other carbon. All right, so in this case now, the number of hydrogens that will be present here is 4 minus 1, which gives us 3. So you do the same thing for carbon 5, you do the same thing for carbon 6, you do the same thing for carbon 7. Carbon 8 is a terminal carbon, and it has just 1 bond attached to it. In other words, for us to know the number of hydrogens, you subtract the number of bonds attached on this carbon from 4. So the number of lines attached on carbon 8 is 1. So 4 minus 1 is 3. So that is why we have here to be CH3. Okay, so you could just pause the video and try to, do this. So I could just help us to number this. This is carbon 1. This is carbon 2. This is carbon 3. This is carbon 4, carbon 5, and carbon 6. So this is 1, 2, 3, 4, 5. Sorry, it's actually not up to 6. So let me just make it up to 6 at once. So we have if you notice, the carbons in between are having CH2, while the ones at the terminals are having CH3. You may want to ask why. Now look up here again. If you look at this this particular compound that did not add hydrogens, this one's here. Now you realize that the terminal carbons, carbon 1 and carbon 8, they have just 1 lines attached to them. So the number of hydrogens that will be present on those guys will be 4 minus 1, which is 3. Unlike carbon 7, carbon 6, carbon 5 that has 2 lines. So 4 minus 2 will give us 2. So that is why here the terminal carbon is having CH3, whereas the middle carbons are having CH2, because the carbons here are having two lines joining it to the two carbons at the side. Okay, so that was this was rule one. What I just did here was to help us understand much better how you can interpret a skeletal or a line formula into the normal form, just in case you're going through nomenclature series and then you get to see this line formula so it doesn't get confusing. All right, so let's dive into rule number two. Now, after identifying, if you notice, this first rule that said identify the parent chain. After identifying the parent chain, you realize that anything that does not fall into that parent chain, I told us earlier, I said it's going to be the branch or the substituent. Okay, and these substituents, they do have a name. All right, so what we're going to be looking at, rule number two, are the possible types of substituent that you can see whenever you're naming an alkane. Now, there are lots and lots of substituents you're going to come across, but we're going to look at the ones that are quite very easily found when you're naming alkanes. Okay, so substituents are also known as branch points. All right, so I said rule number two is for you to identify your substituent. Obviously, once you've been able to get your parent chain, any other thing that is not part of that parent chain obviously becomes a branch point, right? Oftentimes, students don't really know how to name substituent, but don't worry, you're at the right place. Now, the possible substituent that is commonly found in alkanes, possible, right? These are the most common. We have number one is alkyl group, number two is halo group, number three is nitro. Now, what are alkyl groups? Alkyl groups are groups comprising of just only carbon and hydrogen. So if actually they give you a compound and then you're asked to name, and after identifying your parent chain, you see that there is any other carbon. Maybe there is a carbon that did not take part as a parent chain. Obviously, that particular carbon is a substituent. So if that particular substituent is only containing carbon and hydrogen, obviously that becomes an alkyl group. Right, what are the possible alkyl groups we have? If it contains just one carbon and obviously three hydrogens, you're going to have methyl. You may want to ask, why are we putting this dash here? Right, this dash is the point of attachment on the parent chain. Without this compound, this particular CH3, the valency of carbon would not be complete. Remember, if carbon is complete, the valence of carbon is always 4. So if you remove this point of attachment, carbon will now be having 3 hydrogens, which of course violates that tetravalent nature of carbon. So this hyphen you're seeing here is a point of attachment of this alkyl group to the parent chain. Just let's look at this. If you look at this compound here, this C, look at this guy, this substituent are carbon number 4, right? It has just one carbon atom, so the point of attachment is this line here. So that is exact line you're seeing here. So this line is where this CH3 would be attached, onto the parent chain. So I said, if the substituent, after identifying your parent chain, your substituent is containing just carbon and hydrogen, it is an alkyl group, and the common alkyl groups are as follows. If it is one carbon and hydrogen, 3 hydrogens, it's methyl. So anytime you see an alkyl group, a substituent that has just one carbon atoms, obviously that would be a methyl. Okay, we have the second one, B. If it has 2 carbon atoms and hydrogen, it's going to be ethyl. All right, so alkyl group that has 2 carbon atoms, it can be written as CH2CH3, or better still, you just write it as C2H5. Both of them are the same thing because the number of hydrogens present here is 1 plus 1, which is 2, C2. The number of hydrogen present here is 2 plus 3, which is 5. So anytime you see CH2CH3 as a substituent or C2H5, do not forget that is an ethyl group. Okay, let's look at the C part. So we have propyl. For alkyl group that has 3 carbon atoms, It's called propyl, but we have two kinds of propyl. We have the normal propyl, which is this first one, and we have the isopropyl, which is the second one. If you notice, both of them, they all have same molecular formula, C3H7. They have three carbons and 7 hydrogens. So why is this one called propyl and why is this one called isopropyl? I'll explain. Now this is called propyl because the point of attachment of this entire C3H7, this is the entire compound here, this is the entire substituent, right? It is joined to the parent chain using this particular first carbon. So if you want to number this substituent, you start numbering it from the first carbon here, right? Because this is the terminal. You start numbering from the terminal that is closer to the point of attachment. Right, so in this case now, the entire C2, CH2, CH2, CH3, that is C3H7, is attached to the parent chain using this first carbon. Right, whereas in the isopropyl, you notice that this is still C3H7, but this time around, the point of attachment is no longer at carbon 1, but this time around at carbon 2. Please note that you cannot jump and start numbering this guy here to be 1. No, you must start from either of the sides, so which both sides are equal distance. So you might decide to start from the left. This is 1 and this particular guy is 2, or you can start here 1 or 2. So whenever propyl C3H7 substituent is attached to a parent chain, right, using these second carbon atoms, we call it isopropyl. Also, another name for either isopropyl is actually 2-propyl, right? Sorry. I said another name for this is, okay, you may want to ask, why did we say another name for this is 2-propyl? Just like I told us that the entire substance here is attached to a parent chain using using carbon 2, whereas this guy can also be called 1-propyl. The same reason, the entire substance here, molecule, is attached to a parent chain using carbon 1. Okay, so please watch out for any of these substituents. Anytime you see them, do not forget alkyl groups are substituents that comprise of just carbon and hydrogens, and the most common of them is the first four we just finished discussing right now. Okay, so the next thing we're going to be looking at is halo groups. Halo groups are basically halogen groups. Now, if you could remember group 7 of your periodic table, we have the fluorine, the chlorine, the bromine, and the iodine, which is always written as a diatomic, F2Cl2 Br2 I2. But anytime they are acting as a substituents, you no longer call them halogens, or you call them halo groups. All right. Now, because this time around we're just considering just a single atom. Normally, halogen fluorine is always F2, but as a substituent, fluorine will just be F. So instead of it to call this guy fluorine, you now call it fluoro. Anybody that hears fluoro obviously knows that fluorine is actually an attachment on a parent chain. All right. The second member of that halo group is chlorine, which is actually named as chloro. We have bromine, which is named as bromo. We have iodine, which is named as iodo. Okay. The third common substituent we can also find in alkanes are the nitro. All right, so this is nitrate NO2. Do not forget that as long as this is a substituent, there must always be an attachment. It could be by the side, it could be up, it could be down, just to show that this particular substituent is always going to be attached somewhere. It cannot stay on its own like this. It must attach to somewhere. So that is why we have this line written here. Okay, so that's number 2. Number 2 says identify the nature and the type of substituent. All right, so the first one was for us to identify the parent chain. The next one was for us to get to see how to interpret compounds in line forms into their normal basic carbon hydrogen forms. All right, so let's look at rule number 3. Now we've actually gotten to where we start numbering the chain. All right, now oftentimes you've been naming of compounds, you've been seeing 4-methyl, 4-this, 3-this, 2-this. Now, how did we actually arrive at those particular numbers? It is actually through numbering of the parent chain, right? You number the parent chain, and then at the end of the day, you now check which position is any particular substituent attached to. All right, but you don't just number the parent chain anyhow. There are laid down rules and procedures for you to number the parent chain. Okay, so I said number the parent chain from the side that will give the first branching point the lowest number. Okay, remember all these rules are applicable because an alkane has a substituent. Without a substituent, if alkane is just a straight chain, don't be need for us to actually carry out all these rules. Straight chain alkanes, that is 5 carbon is pentane from the second slide. Okay, so we'll say number the parent chain from the side that gives the branching point the lowest number. All right, now rule number 4 says construct the name of the compound. For substituted alkane, compound name is made up of a prefix and a parent chain name. Of course, what's a prefix? A prefix is something that comes before, all right? Something that is always written before the main name. Maybe Mr. Maybe you're a man, you're being addressed as a Mr. You're a lady, you're being addressed as a Miss if you're not married yet, or Mrs. if you're married. So those are prefix, all right? So when you're naming a compound, a prefix is always written first. A prefix is always telling us about the substituent and its position. All right, so before we actually start going further, let's use this example below to explain rule number 3 and rule number 4. Okay, now since I've actually explained what skeletal structure is, I believe you can pause this video and try to interpret this structure in your paper to see if truly you're going to be correct. All right, you never can tell. You might just get this one right. Obviously, you're going to get it right because I'm pretty much sure you followed up in the previous video. Okay, so there are always 2 ways to number a parent chain, right? As long as the chain is not cyclic, as long as it's not a closed chain or a ring form, there are always 2 ways to number an open chain. If the parent chain is actually horizontal, now if you look at this, the parent chain is 6 carbon atoms. You can count that by yourself. And this is this. All right, that is the parent chain. It contains 6 carbon atoms. Okay, in addition to these 6 carbon atoms, if you check it out, there is a branch point. There's something projecting out of what I just circled out now, and that point is here. All right, so this numbering says you have to number the parent chain from the side that would give the branch, the substituent, the lowest possible number. All right, so if you start from I actually labeled this A and B. If you start from the left, we decide with green marker, which is labeled A, this becomes carbon 1, this becomes carbon 2, it becomes carbon 1, it becomes this is carbon 1, this is carbon 2, carbon 3, 4, 5, 6. So if I'm following this side, realize that coming from this A side, the side with green marker, this particular position is a position number 4, right? But coming from the B, the red marker, this position is at number 3. So you ask yourself, which of these 2 positions is the lowest? Remember, the rule says you have to number from the side that gives the first branching point the lowest possible number. So in this case now we have just mono substituted. Mono means 1 substituent on this parent chain. So you're going to start from the side. Remember I told us now that whenever you're numbering a parent chain, you can always come from both sides. Either you come from the left or you come from the right, as far as the chain is horizontal, right? So always come from both ends. Whichever end that gives the substituent the lowest possible number, you actually go with that. So it's very obvious that if you're coming from the red part, this substituent is taking position number 3, but if you come from the green part, the A labeled part, this substituent is position number 4. So I would actually, it's not about me, so the correct way to number this would be starting from B. All right, so we said numbering from B gives the substituent the lowest possible number. Okay, so that is it. So let's look at the next example. I want to name that compound. What I just had to rewrite it. Now look at this. It's the same compound like the one I did previously, but I just had to rewrite it in a way that it will favor me. If you notice, if you check, if I number from this side, this is 1, this is 2, and this is 3, right? But if I choose to come from this other side, right, if I come from this other side, you realize that this is 1, this is 2, 3, 3, and 4. And once again, 3 is smaller than 4. So we're definitely going to go with the side that actually gives it the smallest number. So we start numbering from the left. Now you realize that this point, remember I told us that every end of line represents carbon. So this place is carbon. And for us to know the number of hydrogens present on this carbon, you check the number of lines making contact with this carbon. And it's very obvious that the number of lines making contact with this carbon is 1. So for us to know the number of hydrogens present on this carbon, we'll say 4 minus 1. So that gives us 3. So that means this particular position is CH3. Now if you could remember, the first thing I did here was to identify the parent chain, which is 6 carbon atoms. I started counting from here. I was just checking. You just have to count from one edge to the other to see which one will give you the longest carbon chain. Remember, it must not always be the one on the horizontal. Take note of that. Okay, so in this case, we have identified the parent chain. The next thing we're going to do now is to come back here. Now remember I told us that anytime an alkyl substituent is actually found in a compound. So if you look at this, apart from I circled this part, this was the one that projected out. Right, this CH3 projected out. It's not part of the parent chain. So CH3 is a substituent. And if you could recall what I told us that anytime a substituent comprises of just carbon and hydrogen, that substituent is going to be known as an alkyl group. Right, so this is an alkyl group. And also I could remember I said that if an alkyl group should contain 1 carbon, it is methyl. Let's take us back to look at it here. An alkyl group should contain 1 carbon, it is methyl. If it contains 2, it is ethyl. So coming back to this, you realize that this young man here is a methyl. Alright, so the next thing we're going to do is to name. Remember, in rule number 4, I said if you must name a compound, you have to construct the name, right? How do you construct the name? The name is actually done in such a way that if there is a substituent, the substituent alongside its number would come first, and then the parent chain will come last. Now, what do I mean? Now, it's very obvious now that CH3 is not part of the parent chain, so it's a substituent. And look, based on the numbering system I just told us, coming from the left, we'll give this CH3 the smallest number, which is what the rule told us to do. So we're going to adopt numbering this chain from the left-hand side, which is going to give this first substituent position number 3. All right, so you realize that the parent chain is 6 carbon atoms, right? 6 carbon alkanes is hexane, right? If you could recall, that was the first, the beginning part of this class. I gave us a list of the first 12 straight chain alkanes. Like remember I told us that if you do not understand that, you find it difficult to name branch chains. So this simply means that on a 6 carbon chain, there is a substituent at position number 3. Alright, so anybody that sees the name of this compound would be able to interpret this name to the structure, which means, oh, the parent name is hexane, which is 6 carbon atoms, but on these 6 carbon atoms, I have methyl at position number 3. Alright, so that is how we just did that. So if you look at what I did here, I calmed down to explain this. So I start numbering from the left hand side because numbering from the left gave CH3 position number 3. If I started from the right, this is 1, 2, 3, 4. The right would have given this CH3 position number 4. Alright, so 3 is lower than 4, so we're definitely going to adopt the position number 3 side. So when we complete this guy, we have 3-methyl hexane. Why is it 3-methyl? Because on hexane carbon chain, hexane is 6, we have methyl at position number 3. Okay, so if you look at this, we said that we number the chain starting from the side that will give the substituent the lowest number. This is what we discussed earlier. All right, rule number 5. If you notice what we did previously, this example, we just have one substituent here. But in exams, of course, you're not going to have just only one substituent. You're going to have multiple substituents in some cases. So we look at a case, rule number 5. In a case of where there are multiple substituents, please pardon this English. It's supposed to be in a case where there are multiple substituents on the parent chain, number the parent chain from the side that will give the lowest possible numbers to the substituent, such that the position of the substituent when added would give the lowest possible sum. Okay, I just started with this particular one here. We have two substituents here. Two substituents is very simple, and obviously I don't really need to start retaking what I've taken before now. We have two sides, the B and the A part. All right, so if you start numbering from the A side, we have the two substituents at position 2 and 3. If you add 2 plus 3, that's 5. If you start from B, the two substituents is at position 3 and 4. Right, so this is what we have here. 3 plus 4 is 7, and 5 is lower than 7, so we're going to take this. Remember, our sole aim is to check the side that when you add the top, right, the sum will give us the lowest sum. So 3 plus 4 is 7, 2 plus 3 is 5, so 5 is lower than 7. So if you want to number this particular compound, you start from this side, right, because this side is going to give the substituent the lowest number. Okay, so let's look at try substituted. All right, so I would just allow us to run through the screen. Now I've done the same thing. I have the A part, I have the B part. All right, so if you number from the A part, you realize that the first substituent is at position number 3. The second substituent is at position number 5. There's one thing I like to say here. All right, so if I have two substituents on the same position, right, I'm going to see it as if like the position number will be counted twice. Don't come and say, but we have 2 methyl on position number 5. Why didn't we just take 5? No, we don't do that. All right. You definitely, if 2 substituents is appearing on the same position, you're going to repeat that same position again twice. All right. So in this case now, the first substituent CH3 was at position number 3 when you're starting from the A side. We go to number 5, we have 2 substituents, so we're going to consider this guy individually, 1, 1. So this is 5 up and this is 5 down. So 3 plus 5 plus 5 is 13. If we start from the B side, we have 1, 2, 3. The first substituent, or the second substituent is at number 3. So we say 3, 3. Remember what I told us that if you have 2 substituents on the same position, all right, you have to count that position twice. Don't just say because the 2 substituents on one position, why not we just take one position? No, you will not do that. You have to count it twice. Okay, so if you start from the B side and then you number, you realize that this B part will give us the least possible number when you sum it up. All right, do not forget that we said in the case of multiple substituents from 2 going forward, I'm not going to exceed 3, because if you really understand the first 1 and 2, this 2 and 3 rather, it should really help you to do other ones. You could write it out any way you don't understand, or if you have any question, please make sure you drop it on the comment section. Okay, all right, so let's look at in rule number 4, we saw how to construct a name. All right, so in rule number 6 now, we want to dive into this stuff proper. Now, we say when naming a compound where same substituent occurs more than once, the location of each point separated with a comma is given. Now, this same example I gave us previously, I have repeated it again. Remember, we adopted the side coming from the B, the numbering coming from the left hand side, which is the B. So in this example now, I just decided to just adopt this particular left hand side. I didn't bother writing and showing us how the right hand side will look like, since I already did that in the previous video. Now you realize that methyl is appearing 3 times. Now if you look up to this rule, they said when same substituent, same, occurs more than once, and you realize that methyl and methyl and methyl, they are all the same. So we have 3 same type of substituents, right, attached on this to this chain. So we said in this case now, where we have same kinds of substituents, right, now the position of these substituents, you just have to write them and separate them with a comma. I said the location of each point separated with a comma is given. So after we must have identified the side we're going to number from, we realize that, remember I told us in the previous slide that at position number, if you have 2 substituents appearing on the same position, you're going to repeat that position twice. So at number 3, we have CH3 up, CH3 down. So CH3 is appearing twice on carbon 3, hence the reason why we repeated carbon 3 position twice, comma. Now the next CH3 is at position 5. So realize that we have 3 methyl group, right? So the first 2 is at position 3. So the first one is at 3, the second one is also at 3, the third one is at 5, right? So we said in addition to the number of times it is appearing, right, you have to, the number, in addition the number of times, like after you must have actually done this, you cannot come and say 3, 3, 3, because anybody that sees 3 numbers or 3 position obviously knows that for us to have 3 position here, you must have 3 substituents. You cannot have 3 positions and then you have 2 substituents. It's not possible. So what is now occupying the 3rd position? So we have 3 position here. 2 is at carbon 3, hence the reason why we're repeating 3, and the other one is at carbon 5. So we have 3 substituents here. So if we said in addition, comma, the number of times the substituent group occurs is indicated by prefix. If you look at this particular compound, right, we have CH3 appearing 3 times, 3 good times. So for us to actually name this guy, you represent the position numbers of these 3 substituents that are the same, and then you look through the prefix that's actually suiting for 3. So 3 is tri, so we now say trimethyl. Remember, each of these is methyl, CH3, right, alkyl group with just 1 carbon atom. So in this case now, this is methyl, right, but this methyl is 3, so we now have to add trimethyl. This is now trimethyl heptane. Why is it heptane? Now if you look at this, the whole of this is just the substituent naming. 3, 3, 3. We have 3 substituents on position 3, 3, and 5. The reason why we used comma here is because the 3 substituents are the same. If the 3 substituents were not the same, we would have arranged them alphabetically, right? Which of them will come first alphabetically, write it, and then, but since they are all the same, we just group them together, their position numbers separated with a comma, and then we use tri. Tri simply means 3. So anybody that sees trimethyl, you will know that we have methyl 3 times appearing on position 3, and position 5 on 7 carbon chain. That is where the hexane comes in. Alright, so the parent chain is actually this. That's the parent chain, 7 carbon atoms. Alright, so what if we had a case where it was just 1 or 2 substituents, right? So in this case, it would have just been, assuming we had something like this. Okay, pardon me to just quickly ignore H here. All right, I'm sorry, I just want to name it like this. So this is 1, 2, 3, 4, 5. Now this particular compound, if you look at it very well, we have CH3, we have CH3, Right, so this is position number 1. I can either start from here to call it 1, or I can start from here, because this is also CH3 by virtue of this guy having just one bond. Right, so this is the position 1, this is position 1. So if I choose to start from here, it's still correct. I can choose to start from here, it's still correct, because whichever side I start from here is a number 2, so there's no cause for alarm. Okay, so in this case now, if it was just 2, maybe it would have been 2, 2, because, sorry, 2, 3. All right, because the first substituent is at position number 2, the second one is at position number 3. All right, so you now say di. Di means 2. Dimethyl. Anybody that sees this understands that di is 2. Right, so we have 2 methyls at which position? Carbon 2, carbon 3. Right, on whichever parent chain it's going to be attached to. Okay, so let's look at this particular case. If there are 2 or more different substituents, they are listed alphabetically regardless of their location. So if I have something like, let's say, CH3, CH, I have chloro, I have CH2, I have CH3, methyl, I have bromo. Okay, let me extend this again. Okay, wait, let me just stop here. So this let's look at this compound. This the parent chain here. Okay, let's increase this guy like this. I just want something that will be a bit easy for us, since we are still trying to take it little by little, so that for you to understand. All right, so we have this. I just hope this was what I wrote here earlier. So we have this compound, and you're asked the name. The very first thing that should come to your mind, look at the compound to identify the parent chain. Count from each edge to each edge to see which way the one gives you the parent chain. So you realize that if you count from here, that becomes the parent chain. So this is 1, 2, 3, 4, 5, 6. This is 6 carbon parent chain. These carbons. All right, so we've done this. The next thing we are going to do is to number the parent chain. Or first, before you proceed to numbering, you should first of all look at the various substituent that is present here. We have bromo, we have CH3, we have chlorine. Why do we call this guy substituent? Because it is not part of the parent chain. The parent chain is the one I circled with yellow ink. So anything that is not part of this yellow ink is basically a substituent. All right, so since we've actually known the different substituents that we have here, the next thing you're going to do is to number this parent chain. Remember the rules when numbering. You must start from the side that will give the substituent the smallest number, such that when added, the positions will actually give us the least possible sum. All right, so in this case now, I've already run through it with my eyes. It's very obvious that if we start from here, we'll get the possible sum. This is 1, 2, 3, 4, 5, 6. If I want to add this up, this is the first substitution is at position 2 plus 3 plus 4. That is 9. So if you want to start from this other side, so this is 1, 2, 3, 4, 5, 6. So if you want to start from this side, we see the first position coming from the left is at position number 3, plus the second one is at number 4, plus the third guy is at number 5. So when you add this together, it gives us 12. So this side we are going to follow, this side we're not going to follow. All right, so now we've actually noticed that, so I want to clean this. We've noticed that we have three different substituents here. Remember what I told us previously, that in a case where you have in the case where you have different substituents that are not the same, not previously, is on the screen. If you have two almost different substituents, when you're naming, remember substituents are always written first before the parent name, right? You have to arrange them alphabetically. So after our numbering, you're going to follow this side, right? So realize that we have at position number 2, we have bromo. At position number 4, we have methyl. At position number at position number 3, not 4. At position number 3, we have methyl. We have this. We have this. At position number 4 as well, we have chloro. Now, if you look at these three substituents alphabetically, the one that comes first is B. Remember we said regardless of the position, we don't look at the numbers. So the one that comes first is B. B comes first alphabetically. After B is C, then M. So we're going to arrange this guy alphabetically. So we go by saying this becomes 2-bromo. Right. So anytime you're writing a letter and a number, you must separate them with an hyphen. 2-bromo 3. Sorry, not 3. And after bromo is chloro, because chloro comes first alphabetically before M, regardless of the position number. So this is 4-chloro, and then 3-methyl. The parent chain is 6 carbon atoms. So if you could recall, 6 carbon alkane would be hexane. Alright, so this becomes the name of this compound. Alright, so we have 2-bromo, 4-chloro, 3-methyl, hexane. Alright, class. Alright, guys, so for this particular edition of this video, I'll stop here, and then I'm going to post up again the continuation of this so we can dive more into this. One is more like for beginners, so we're going to dive deeper and then see a case whereby they give us multiple substituents. All right, so please make sure you actually like and subscribe. Thank you very much in advance. Please, if you're a newcomer, please do well to hit the subscribe button below. You can just do it now, right? You can just take 1 second to just do it, and please don't just tap. All right, you can share the videos to your friends. So let me know what you think about the video. If there's anything you think I should improve